Section 7.4, Estimating the Population Mean Sigma Not Known. In the previous section, we learned how to find a confidence interval if the standard deviation were known. In most instances in real life, the standard deviation is not known and usually cannot be accurately estimated. As long as the previous requirements are met, we can still find a confidence interval using the student's t-table. Just as before, x bar will be a good point estimate for the population mean, mu. Now the student's t-distribution behaves in a very similar manner to the standard normal distribution. So we still have that bell-shaped curve. The t-curve, though, tends to get wider at the tails faster. So it has a little bit more variability in it than the normal distribution. So just like with the standard normal table and z-scores, we have to standardize our scores here. But instead of z-scores, we will call them t-scores. Very similar to that formula, we have our random variable x. We're going to subtract off the population mean mu and divide by s divided by the square root of n. Now we just said we're using this method because we don't know the standard deviation, but here the standard deviation s appears in our formula. Well, since we don't know the standard deviation, we're going to use the sample standard deviation s as an estimate. But because it is an estimate, it's not the true population standard deviation. That introduces more error into our interval, and that makes our confidence interval a little bit wider. But we're still going to use this method. Now, once we've standardized our scores, we will look them up on the student's t-table, or t-table for short. So you won't hear student said quite as much, just t-table. One additional piece of information we need to look up something in the t-table is degrees of freedom. We didn't have to do that with the standard normal table, but we do have to do it here with the student's t-table. The degrees of freedom is the sample size less 1, or n-1. So before we get to worrying about confidence intervals, let's practice looking up values on a t-table. So example 1. Find the following values on a t-table. Example A, n, the sample size is 6, alpha is 0.01, and this is going to be left-tailed. Now, it's a good idea, just as we did with the standard normal, to go ahead and draw a picture. And if we're in the left tail, that means we're somewhere over here, and this alpha of 0.01 is telling me that the area in the tail is 0.01. So something really small. Maybe my picture is not quite to scale, but I for sure know that we are on the left. So we know the area there is 0.01. Remember, we also need the additional information of degrees of freedom. And here that will be 6 minus 1, or 5. So now I go to my student's t-table, and this is located in the back of your book in the appendix, or with the tear-out card that comes with your book. So degrees of freedom are 5, and notice that's the first column here on the side. So I'll go down to 5, and then I'm going to go over until I am under 0.01 for area in one tail. So notice we have area in one tail and area in two tails. So here's 5 and here's 0.01, and the value that falls there is 3.365. So the t value is 3.365. Now here's where our picture might help us out a little bit. Remember, we're on the left, and we're to the left of the mean, so that means this value has to be negative. So with the t-table, there's not negative versus positive values the way we had with the standard normal table. It's symmetric, just like the standard normal curve was. So we just have to know, are we on the left or are we on the right, and then use a negative sign or don't use a negative sign as appropriate. Okay, let's take a look at B. This time the sample size n is equal to 10. Alpha is equal to 0.05, and we are right-tailed. So if I draw my little picture, I'm in the right tail, so I'm over here this time. And that area is 0.05. Well, this time my degrees of freedom will be 10 minus 1, or 9. And we're looking for the t-value that goes right here that would give me an area in the tail of 0.05. So I go to my table, and first I look for degrees of freedom 9, which is here. And I'm going to be under 0.05. Be really careful. This is 0.005. We want 0.05, which is here. So 1.833. And that will be positive since we are on the right. Finally, we have C. N is equal to 17. Alpha is 0.02, and we are two-tailed. So this one's going to be a little bit different. What we're saying here is that we have two tails, and that the total area for these two is 0.02. So what would that mean for the tails separately? They would each be 0.01, and our table actually gives us both, and we end up with the same value. So the total area is 0.02 if I'm talking about both tails, or if I'm talking about a single tail, 0.01. But just like before, we still need our degrees of freedom, which will be 17 minus 1, or 16. So here on our table, I'll go down to 16. And area in two tails, notice how area in two tails is exactly the same as area in one tail, 0.01. So I'm here at this value, 2.583. So T equals 2.583, but because we actually are in two tails, we also have negative 2.583. So that should be a little bit of practice of looking up values on the t-table. Well, once we do find that critical value on the t-table, we can find the margin of error. And then resulting from that, we can find the confidence interval. So these formulas should look relatively familiar from what we've been doing with our previous confidence intervals, where we take x bar and subtract off the margin of error, or take x bar and add on the margin of error. That creates that confidence interval. But as far as calculating E itself, instead of a z value here, we're going to have a t value. And we have the sample standard deviation divided by the square root of n. So let's try this out. Example 2. The number of grams of carbohydrates in a 12-ounce regular soft drink is listed below for a random sample of soda brands. Estimate the mean number of carbohydrates in all brands of soda with 95% confidence. So when it says that, estimate the mean number with 95% confidence, that's basically saying find a confidence interval. But for us, we know we have these preliminary calculations, so let's get started on that. So the first thing we need to do is find the mean and standard deviation. And as we learned before, it'd be a good idea to use your calculator to do that. So if you want to pause the video here and go ahead and input in your calculator, make sure you still remember how to do this. Whether you have a basic scientific calculator or a graphing calculator, you want to find the mean and standard deviation. Okay, so after I put everything in my calculator, I found that the sample mean was 41.6. and the sample standard deviation was 5.99. It's also worthy to note that the sample size, because we do need that, is 20. Now the next thing I need to do is look up the T critical value. Okay, now because it didn't specify being bigger than the mean or smaller than the mean the way we had in the previous problem, right tail, left tail, we're just going to look up and assume this is two-tailed. So we're going to do two-tailed with degrees of freedom. Remember, that's one smaller than the size of the sample, so that would be 20 minus 1, or 19. And alpha comes from the confidence level, so that's 1 minus 0.95 that they told us, or 0.05. Now, I don't know that we need a picture necessarily here. If we've kind of got the hang of two-tail, that you can draw one if you want to, but I think we're okay. So on my t-table, I'm going to go down to degrees of freedom 19 and go under 0.05 on the two-tail test for my critical values. So here I am at 19 and 0.05, so that takes me to 2.093. Technically, I get a positive and a negative value, but because we're going to use this for the margin of error and we end up subtracting and adding anyway, I'm not going to bother to keep track of those. So that's my critical value. Now, we're going to calculate the margin of error. So in our above formula, for E, we're going to take that t-value, 2.093, times the standard deviation, 5.99, divided by the square root of the sample size, which is 20, and we get 2.80337 if you keep a couple of different places. So that's the margin of error. And then for the confidence interval, we would take our mean, which was 41.6, and add on the margin of error. And we would also take it and subtract off the margin of error. So our 95% confidence interval would be 38.8 if you round to the nearest tenth for the lower bound, and 44.4 for the upper bound. And remember, for our interpretation, we would say we are 95% confident that this interval contains the true mean. Remember to be very careful not to say we're 95% sure that the mean falls into that interval. That's not the correct way to say it. So we're 95% confident that this interval, 38.8 to 44.4, contains the true mean of the population of pretty much all sodas and the number of carbohydrates that they have, or the average of carbohydrates that they have. Okay. Well, we've done quite a bit with confidence intervals. We looked at when it was normal, when we knew the standard deviation, when we didn't know the standard deviation. So it can get kind of confusing to know when do I use which one. Well, here's a little chart, a little flow chart to help you know which one you're going to use. The first question you want to ask yourself is the population standard deviation sigma known? So we're not worried about knowing the sample standard deviation, but of the population, do I know sigma? If yes, then go ahead and use a z-value no matter what the sample size is, whether it's small or large. Just be careful though, even if the sample is small, it still has to be approximately normally distributed. So there should be some bell-shaped curve to what's going on. So let's say you ask yourself, whether the population standard deviation is known, and it's not. It's stated that the population standard deviation is unknown. Well, then you have to ask yourself a second question. Is the sample size equal to or larger than 30? If it is, then go ahead and use a z-value. So basically what this is saying is if the sample is sufficiently large, so more than 30, then you can use a z-value even if you don't know the population standard deviation. But if the sample is smaller than 30, that's when you want to use a t-test or t-values. So typically if we don't know the standard deviation and the sample is small, we're going to use the t-values. But again, you want to be careful. If we're less than 30, then the variable should be normally distributed. Okay, let's take a look at a problem. This is very similar to something in your homework with deciphering when and which test to use. So let's say you want to estimate today's mean temperature, and you take a series of measurements or a sample throughout the day. The mean of those measurements is 63.5 degrees Fahrenheit, and their standard deviation is 3.8 degrees Fahrenheit. So remember, this is coming from the sample. For each of the following sampling scenarios, determine which test statistic, there should be IC there, is appropriate to use when making inference statements about the population mean. Okay, so a little bit of backtracking here. This has to do with the central limit theorem. And the central limit theorem says that no matter how the original distribution started off, whether it was skewed to the left or skewed to the right, whether it was normal or uniform or anything like that, when I start to take little groupings of the mean, the distribution of the means is going to behave like a bell-shaped curve. So that's what this is based off of. And we're going to look at a couple scenarios here where maybe the sample is small and we know the standard deviation, or maybe it's large and we don't know the standard deviation, all kind of combinations like that. And we need to make a decision of which sampling technique would be appropriate. So keep in mind this has to do with the central limit theorem, and when we're talking about the mean, the distribution of the mean of an original distribution, even if the original was not normally distributed, the distribution of the means is. Okay, kind of bear with me here. A, the sample has size 13. It is from a normally distributed population with a known standard deviation. Well, think about the flow chart we just talked about. The first question I want to ask myself is the standard deviation known? And here they're telling us that it is known. So I really don't even have to consider the other information. Because the standard deviation is known, I can go ahead and say that I'm going to use a z-test here for z distribution. Well, we do still want to know about it being normal. That's still important. But if we know that we have the standard deviation, then we can automatically go ahead and use the z distribution. Okay, take a look at B. The sample has size 20, and it's from a population with a distribution we know little about. Well, if we don't know any other information, it kind of makes it hard to make a decision. We don't know if it's normally distributed. We don't know whether or not we know the standard deviation. So this one is too little information or unclear. So we can't make a decision here about which distribution to use. Not enough information. About C. The sample has size 80 and it is from a non-normally distributed population. Okay, so let's go through that chart again. Do I know the standard deviation? Well, they're not telling it to us, so we'll have to assume that we don't know that. So then I ask myself if the population is larger than 30. Well, yeah, it is. So since it's larger than 30, then I would use the z test. But because we don't know the standard deviation, I could also use the t-test. So this one could be z distribution or t distribution. So the reason why it's or is we have two reasons. Because it's so large, since 80 is so much larger than 30, that gives me the permission to use the z distribution. But because I don't know the standard deviation, I could use the t distribution. And actually here we would get very, very close or similar results using either distribution, because a t-distribution actually starts to look like a standard normal curve the larger our sample size gets. So this one could go either way, z or t. Let's take a look at D. The sample has size 14, and it is from a normally distributed population with unknown standard deviation. So I'll go back to the top of my flowchart. Do I know the standard deviation? No. They told us we do not know. So then my next question is the sample size larger than 30? Nope. 14 is definitely less than 30, so that means this will be a t-distribution. Okay, and finally, E. The sample has size 95, and it is from a non-normally distributed population with a known standard deviation of 4. Do I know the standard deviation? Yes, they told us it was 4. So this is Z. Okay, so practice a little bit understanding when do I use a t, when do I use a z. Pretty much for t, you're looking for small samples or that you don't know the standard deviation. And for a z-score, you're either looking for very large samples or you know the standard deviation.